He worked as a reviewer of 18 reputed international journals. Number of books published are 6. He has total 85 research publications, including articles, journal publications, conference proceeding publications. Due to the constraint of time, I briefly introduce him. Thank you, sir. Thank you very much. I welcome you, sir, from the bottom of heart. I request you to please deliver the invited talk. Please, sir. Thank you.
Thank you, Vadadkar sir, for your very kind introduction. So, I'm very happy to be here for this invited talk. So, I kindly request the technical committee to open the presentation file. So, today I'm going to present my research work on sawdust polystyrene based pellets and silica polystyrene based leaf mesh for effective oil water separation. Yeah, thank you. So, my affiliation is Self-Cleaning Research Laboratory, Department of Physics, Rajaram College. And I'm very grateful to the organizing committee members of the second international conference on recent advances in material science and technology. And Department of Physics, GS20 Arts, Commerce and Science College, Chandrupazar, Amaravati, which is organized in collaboration with IPSC Sant Gadge Baba Amravati University, Amravati. Next. Can you go back? Okay, next. Okay. So, coming towards my research problem. So, I'm working on a super hydrophobic coatings for self-cleaning and oil water separation. So, the basics of this super hydrophobic research comes from like many extraordinary things happens in nature. Like the lotus leaf is very water repellent. It repels the water very strongly. So uh, you can see that on the lotus leaf, the water drop takes a round shape like a cricket ball and easily roll off on the surface. So it won't spread on the lotus leaf. So any dust particle accumulated on this lotus leaf, they are taken away from the rolling water drop. So the lotus leaves are self-cleaning, so they clean themselves. So that's why lotus leaf is called self-cleaning surfaces. The next one. So, okay, just as a visualization, in Asian culture, lotus leaf is known as a symbol of purity, and you can see that many gods like lotus flower because the lotus leaf cleans itself. So that's why many gods also like the lotus leaf. Next. Okay, so why this lotus leaf is extremely water repellent? So there is a German botanist, Professor William Bartlett. So in 1997, when the scanning electron microscope was developed, so he observed the morphology of the lotus leaf under the scanning electron microscope. And what we observed that, so the lotus leaf has micro scale roughness, and these micro scale papilla are covered with the nanoscale wax material. So there are two ways by which lotus leaf shows the suprahydrophobic or extreme water repellent characteristic, because in the rough structure, the air can be trapped, and the nanoscale wax material, which is a hydrophobic in nature. So this two means surface roughness and the chemical structure both combinedly gives you the extreme water repellent property of the lotus leaf. So it was observed and analyzed by the Professor William Bartlett uh, using the scanning electron microscope. Next. So there are different types of weighting on solid surface. You might be knowing the Young's model for the flat surface. When you put the water drop on the flat surface, flat smooth surface, the water drop spreads on smooth surface because there is a high adhesion between the solid and liquid surface. But Wenzel proposed a theory, and he said that if you rough the smooth surface, then the contact angle of any liquid may change, and it will change in a positive direction, like the contact angle will increase on rough surface. And it was proven that yes, the contact angle is increased above 90 degree, and such surfaces are called as hydrophobic surface. So hydro means water, phobic, phobia means you are afraid of something. So these surfaces are afraid of water. So these surfaces are named as hydrophobic surfaces. Now, in the next, Cassie and Baxter, these two scientists said that, okay, I can tune the roughness in a such a way that in this rough structure, you, the tiny air pockets can trap over here in this rough protrusions. So that these air pockets won't allow the water drop to sink inside the protrusions. So that the water will water drop will leviate on this superhydrophobic surface. So the contact angle will be more than 150 degrees. So hydrophobic surface, superhydrophobic surface, the main difference is the contact angle, water contact angle. So on the superhydrophobic surface, it shows more than 150 degrees. So it is called as a superhydrophobic surface. Next. So now how self-cleaning works on the superhydrophobic surface. So if you take a normal smooth solid surface like you can see on your left, so if any dust particle accumulate on this smooth solid surface, then the sliding water drop cannot take away all the dust particle while sliding, because the adhesion between the dust particle and the solid surface is very high, so that the sliding water drop cannot catch all the dust particles. On the contrary, on the superhydrophobic surface, the adhesion between the solid dust particle and the solid surface is very low, and the rolling water drop can catch all the dust particles and take away while rolling down. Next. So there are many ways to prepare such a self-cleaning superhydrophobic coatings, and many polymer and nanoparticle composite you can use it using deep spin spray coating, which are the simplest one. You can go to another complicated deposition techniques, but these are deep spin and spray are one of the cheapest way to coat on the any solid surface like glass, metal, fabric, plastic, metal, wood, and paper. Okay, next. So there are many industrial applications of this self-cleaning superhydrophobic coatings. So, just to evaluate on the window and door glasses, you can apply the body of vehicle, windshields of the vehicle, underwater cameras, fabrics, sport materials, anti-corrosion metals, traffic indicators, solar cell panels, electronic materials, roadside convex mirrors, wood surface, and many. The list can be extended to highest number, but I'm just limiting to some of the different uh, applications. Next. So now coming towards the today's presentation, there are many key issues faced around the world. One is the oceanic oil spill and industrial oil spill in the river. So sometimes the oil spill inside the ocean, maybe because of the oil carrying boats can the accidents and the oil spills on spilled on the ocean surface, water surface. So what those affect on the environment you can see on this below. So many fishes and the oceanic uh, constants, they affect very badly because of the oil pollution. And there are many other factors too, which oil can affect on the marine environment. Next one. So now to take out this oil from the water, we have in the superhydroponic process two ways. One, you have to take the polyurethane sponges, modify it with the superhydrophobic material, and this superhydrophobic material can catch the oil but repel the water. So such surfaces can be prepared using the sponges. Next, you can use the stainless steel mesh as a main bed, and you can put this nanocomposite superhydrophobic coating on this stainless steel mesh, and you can pass this oil water mixture through this mesh so that you can separate the oil from the water. Okay, next. But as I said, sponges using sponges or stainless steel mesh as a substrate. Of course, the polyurethane sponges are not so costly; they are cheaper. But stainless steel mesh, those are very costly. For 1 meter by 1 meter stainless steel mesh, it can cost maybe around 5,000 to 10,000 rupees. So, what I suggested, like in our college, when I given the project to the master students, they said that we don't have the polyurethane sponges and we don't have even the stainless steel mesh. So I suggested them use the sawdust as a nanoparticles and to bind this sawdust inside this nanocomposite use some of the polymers. So they use the polymers, different polymers, and we find out that polystyrene is the best polystyrene which can form the pellet of the sawdust. Next one. So you can see that what we did, we collected the sawdust from the sawmill, and this is the raw sawdust you can see on the petri dish. We filtered it using the stainless steel mesh of the pore size of 50 nanometer. So whatever the collected sawdust we have now, after drying, those sawdust are of size of 50 nanometer. Now what we did, this sawdust was uh, mixed in the polystyrene and make the sawdust polystyrene composite and keep it for the overnight drying. So we get the pellet, sawdust polystyrene pellets. So these pellets can be used for the oil water separation. So you can see the setup of oil water separation. So this is just put it in this setup and pass the oil water mixture to this pellet. So you can easily separate the oil from the mixed water. Next. So this is some of the experimental work where we keep the constant concentration of the sawdust and the polystyrene concentration was varied. So uh, you can see that we have varied the polystyrene concentration from 50 milligram per milliliter to 150 milligram per milliliter to just check out what is the effect of polystyrene on the preparation of the pellet. Next, so this is the sawdust pellets. After drying, sawdust and polystyrene pellets, you can see such a very 2 millimeter thick pellets you can get it, and it is a freestanding, robust. It won't break easily. Okay. So next one. So this is the surface morphology of sawdust pellets. You can see the sawdust particles in the image of A. Uh, you can see that, as I said, it is around 50 nanometer of the diameter. So you can see that SP1, SP2, SP3 samples, where you can see the nanocomposite is formed by the polystyrene and sawdust particles. And we found that SP3 pellets where the polystyrene composition was 100 milligram per milliliter was best sample. Next one. So you can see that we varied the concentration of polystyrene from like 50 milligram and 75, 100, 150. So for the lower concentration of polystyrene, so the pellets form was not flat, those are curvy because the concentration of the polystyrene is very low. And while drying, it won't dry very uniformly. So we can see the curvy pellets. And as we increase the polystyrene concentration, on the same side, the contact angle goes on increasing. So for 50, it is 123 degree. For 75, it is 135 degree. And for 100 milligram per milliliter of polystyrene, we got 152 degree of the contact angle. So we get this concentration as a final concentration of polystyrene in the nanocomposite. So you can see we throw this pellet on the water, so it is floating. It is not sinking down. So it suggests that so these pellets are super hydrophobic in nature, and it can now you can see these oil drops. So oil drops are making zero contact angle. There is no measurable contact angle of oil. So next. So what we did, as I said, while explaining the surface morphology of the lotus leaf, that air can be trapped inside the rough structure. So as a uh, matter of concern, what we said that uh, we put the pellets inside the water, so you can see the shiny plastron layer. So this shiny plastron layer, it is because of the air trapped inside the rough structure of the pellets. And when we put some oil in it, so oil get absorbed inside the pellets, and the air is slowly come out of the pellets. So this is just an idea experiment we did. So next. So this is the oil water separation by this prepared superhydrophobic sawdust pellets. So we could have sufficiently or significantly separated the hexane. So this is the A line is the hexane we separated from the water. Then we separated the kerosene from the water. Then diesel and coconut oil. So these mixture of oil vaporization was completely separated by this prepared sawdust polishing membranes. Next. So we have calculated the oil water separation efficiency of this sawdust pellets and how many times we can use these pellets for oil water separation. So we observed that the hexane was separated around 98% of the hexane was separated. Kerosene, it also 98%. Diesel also 98%. Coconut oil, it is around 95%. Maybe it is because of the viscosity of the oils. So highly viscous coconut oil may be got trapped inside this sawdust pellets, and that's why the separation efficiency is lower. But how many times hexane can be separated through these sawdust pellets? So around 35 times. After 35 times, the sawdust pellets are not used for the oil water separation. For the kerosene, it is around 30 times, diesel around 28 times, and coconut oil around 15 to 18 times. So this is the separation efficiency, and number of separation cycles can be used for different oils. Next. So sometimes what happens, the oil get mixed in the muddy water also, like river water. So how to separate the oil from the muddy water? So this was also the challenge in front of the researcher working in this field. So we also tried this by taking muddy water, mix it in kerosene, and we efficiently separated. You can see the kerosene was efficiently separated from the muddy water. So we put around 20 ml of the kerosene inside the muddy water, and all the 20 ml kerosene was efficiently separated from the mixture. Next. So we also performed another experiment where the mixed oil can be separated from the warm water, hot water. So the kerosene which was mixed in the water, which is kept at a temperature of 50 degrees Celsius. So this kerosene was efficiently separated from the hot water also. Next. So the mechanical durability of the superhydrophobic sawdust pellets was also checked. So for this, we use the adhesive test and the sandpaper adhesion test. So for this test, the pellet shows highly mechanical durability, and it is superhydrophobic in nature. Next, uh, as I said, the mechanical stability by taking the knife, which scratches some of the part of the pellets and observe the wettability of the pellets. So we observe that the pellets are super hydrophobic even if stretched for inside of the pellets. So having the good mechanical durability. Next. So conclusion, as I said, so the 50 milligram, sorry, 100 milligram per milliliter of polystyrene and the sawdust of 100 milligram. If we prepare the nanocomposite of this, we can get the oil water separation membranes using sawdust. It is a 3 for 1, and it can be industrially used. The commercialization can be possible. Next. Next. So as I said, the stainless steel mesh is so expensive. So for the stainless steel mesh as a substitute for the stainless steel mesh, what we use is the leaves of the teak wood tree. Next. So you can see that the green teak wood leaf would look like this. And if you dry it, so you can see the mesh-like structure of this teak wood tree. And now this leaf mesh was used as a mesh membrane for the oil water separation. So what we did next, so here we use the silicon nanoparticles and polystyrene nanocomposite to coat on the teakwood tree leaf mesh, and you can see that the such a superhydrophobic leaf mesh can separate the oil from the water. Next. So these are the experimental conditions. Like as I said, 10 milligram per milliliter of polystyrene solution was prepared, and the coating solution containing different concentration of silicon nanoparticles, like getting from 10, 20, 30, and 40 milligram per milliliter of hydrophobic silicon nanoparticles in pH solution was prepared and coated on the leaf mesh by deep coating. Next. So this is the leaf mesh, as I said, and the dried leaf mesh was cut down. So you can see that dried leaf mesh and the surface morphology of the dried leaf mesh, and you can observe the porous structure of this leaf mesh. And yeah, this porous surface is sufficient for us to coat on the hydrophobic nanocomposite material on this leaf mesh. Next. So this is the dried leaf mesh and silicon nanoparticle and polystyrene modified leaf mesh. which looks like this optically. Next, this is the surface morphology after coating. So this is the dried leaf mesh. As I said, it is a porous structure, and after the uh, coating of the silicon nanoparticle in polystyrene, so you can see the crater-like structure. So these holes are there uniformly of different sizes, of course, uh, uniformly covered on the leaf mesh, and the oil can pass through these holes, and the water is remaining behind. Okay, next. So the wettability of the leaf mesh, it is nearly superhydrophobic. Next. So this is the setup for oil water separation. So two beakers are taken. One beaker, we have put the downside this leaf mesh, and we put the oil water mixture inside this beaker. Next. So you can see that the contact angle on the superhydrophobic leaf mesh will be 162 degree, and oil contact angle will be 0 degree. So from this mesh, you can separate the oil because it is absorbing the oil and repelling the water. Next. So gravity-based oil water separation was performed. Here we have separated five kinds of the oils. One, petrol, which was sufficiently and efficiently separated. Kerosene, diesel, coconut oil, and last, lubricant oil. So lubricant oil is little difficult to separate because it is highly viscous. So these five kinds of the oil, we try to separate it, and we successfully separated it using the lead finish. Next. Uh, Now, gravity-based oil water separation has some issue because in the gravity-based oil water separation, first you have to add the oil and drain water, but in the tilted oil water separation, both the mixture, oil and water mixture, uh, you can put it at the same time and you can separate it efficiently, like petrol, kerosene, diesel, coconut oil, and lubricant oil. All the oils are efficiently separated, and by some quantitative data, next, for the quantitative data, you can see that next oil water separation efficiency and reusability. So separation efficiency was changing as per the viscosity of the oils. So you can see that for the petrol, it is a 98% separation efficiency. For kerosene, around 98%. Diesel, it is around 98%. Coconut oil, around 96%. Lubricant oil is around 88%. But if you can see the reusability, for all the up to diesel, petrol, kerosene, and diesel, they show around 20 to 24 times you can reuse these membranes. But for coconut oil, you can use it 18 times, and lubricant oil only for 4 times you can use this membrane because it can damage the membrane, lubricant oil. So these are the reusability of the uh, superhydrophobic lead mesh. Next, so this is the conclusion that yeah you can observe that so different types of the oils can be separated through this leaf mesh. So the challenge is this. This is the teakwood tree leaves we have used for this oil water separation as a membrane. But maybe there are many other stable leaf meshes available in nature, and we can make use of these meshes for the uh, to prepare cheaply uh, available oil water separation methods. Next. Okay, I must thanks acknowledgement for the GS College for giving me an opportunity to deliver the innovative talk in the second international conference from 2022. I must thank Chairman Principal of this college, Dr. R.S. Ramtekesar, GS Mahitya Thank again, Professor Dr. S. A. Vagunesar, Director of IPSC, Sant Gadgavabhai, Amravati University, Amravati. I must thank convener of this conference, Dr. D.R. Dislocation, Department of Physics. Also organizing secretary Dr. P.S. Rovenera. Also the co-conveners Dr. A.V. Rajguru, Department of Physics, Mrs. Hemen Pawar, Dr. A.R. Banso, Dr. U.P. Manik Madam, for your uh, giving me an opportunity to present my research work. Next, yeah, I must thank you all. Thank you so much.
Now the session. Question.
Yeah, please.
Yes, sir. Palette. And you have
As you said, so yes, if you for the optimum concentration of polystyrene, as I said, 100 milligram per milliliter of polystyrene absolutely increases the contact angle of this sawdust polystyrene membrane, because the polystyrene act as a low surface energy material, which is a hydrophobic in nature. Of course, all the polymers are hydrophobic in nature. Uh, what makes it superhydrophobic is that the roughness provided by this sawdust particles. So both roughness and this polystyrene gives you the higher contact angle, water contact angle. Yes, sawdust carbon behaves as a nanoparticle.
sir. Thank you for wonderful lecture. I am very much thankful, sir, for giving such moment. Thank you. Thank you very much.
Namaste, sir. Thank you, sir.
Very different topic also.
Yes, sir. Superhydrophobic.
एक क्वेश्चन आहे, आपले जे फिल्टर्स आपण जे यूज करतो, डस्ट फिल्टर्स,
हा.
जनरली वॉटर
हां
प्युरिफिकेशन,
हां
त्याच्या कंपॅरिझन मध्ये याची इफिशियन्सी जर आपण जर केली तर
वॉटर प्युरिफिकेशन नाही, तुम्ही एअर प्युरिफिकेशन
नाही, वॉटर प्युरिफिकेशन जे आपण करतो
नाही, त्यामध्ये मेम्ब्रेन टेक्नॉलॉजी यूज केली आहे. आम्ही तेवढ्या खालच्या मेसोपोरस म्हणजे 100 नॅनोमीटर पेक्षा खाली जाऊ शकत नाही.
नेचरमध्ये आपण अप टू 100 नॅनोमीटर.
हा, अप टू 100 नाही, कारण सगळे जे काही त्याच्यामध्ये मिक्स झालेले जे पोल्युटंट आहेत ते 100 नॅनोमीटर पेक्षा साईज खाली असतात, त्यामुळे ते अडकून राहतात त्या मेम्ब्रेन मध्ये.
याचं ऍब्सॉर्बन्स तुम्ही काढलं नाही पर्सेंटेज ऑफ ऍब्सॉर्बन्स whenever it is separation is there.
ऍब्सॉर्प्शन काढलं आपण, सेपरेशन इफिशियन्सी बघितलं ना, ते कम्प्लिटली 100% नाही आहे, 98% आहे. तर 2% हे जे काय ऍब्सॉर्प्शन
त्याची तुम्ही स्टडी केली आहे का ऍब्सॉर्बन्स?
म्हणजे 98% मधलं मायनस म्हणजे
सर स्टडी केलेली आहे का ऍक्च्युअल तुम्ही
तसं आम्ही किती पर्सेंट ऍब्सॉर्प्शन
मिनिमाइज ऍब्सॉर्प्शन?
हा हा, तसं होय. बरं, ते नाही, ते अजून नाही, ते नाही. ते
याच्यामध्ये अजून काही जसं तुम्ही जे कंटेंट वापरले वगैरे किंवा असं
होऊ शकतं. तेवढं क्रिटिकल आम्ही नाही केलं, कारण हे सगळं वर्क जे आहे ते इनिशियल PhD वर्कनी केलेलं आहे. त्यामुळे ह्याच्यामध्ये अजून होऊ शकतं. हो हो.
डॉक्टर SS कवर
कवर
सिनियर कॉलेजला प्राध्यापक आहे.
होय का मूर्तिजापूर yes, yes.
अकोला अमरावती रोडला
हो 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 हो
डॉक्टर आडगे वारले.
ह्याच्या आधीचं स्टेशन ना मूर्तिजापूर म्हणजे बडनेरच्या आधीचं हो
तुम्ही वाया
हो हो तिथे हो ट्रेन आता
Now it's my name is Amar. Privilege to introduce our person of plenary talk, Dr. Devraj Singh sir. Devraj Singh is a professor and head department of physics and director of Professor Rajendra Singh Institute of Physical Sciences for study and research. Veerbhadra Singh, Purvanchal University, Uttar Pradesh, India. He obtained his DPhil in science at University of Allahabad, India in 2002 on the study of ultrasonic attenuation in condensed materials. His research and publications interest include the mechanical, thermophysical, ultrasonic characterization of condensed and advanced materials. He is fellow of Ultrasonic Society of India and life member of number of scientific societies like IAPT, Indian Association of Physics Teachers, Acoustical Society of India, Materials Research Society of India, Meteorological Society of India, Indian Physics Association, Iron Beam Association of India. He is the associate editor of Journal of Meteorology Society of India, Springer, and member of editorial board of the Journal of Pure and Applied Ultrasonics, Journal of Acoustical Society of India, Journal of Applied Physics, with 19 years teaching and research experience. He has, to his credit, more than 100 research articles in national as well as international journals of ultrasonic and material science, and 24 books including fundamentals of optics, applied optics, modern physics for science and engineering, thermal physics, electronic devices, engineering physics. These books are published in his credit. Sir, I heartily welcome you and request you to please deliver the plenary talk. Please, sir.
मैं अनंत वडक्के ऑनलाइन के लिए अटेंड
Thank you, Anand sir. I am very much thank you to organizers of this conference. This is Raman series. This is second series, and I am highly thankful to principal of this college, Dr. Ram Deke, and convener Vijay Dr. Pawar, Bagli sir, and other members of the organizing committee. Friends, today I will talk on elastic, mechanical, and thermal properties of rare earth materials. As you know, in periodic table, you will see lanthanide and actinides. There are many elements in those series, and I studied, and especially one of my students did work on rare earth materials. And today I am presenting here on rare earth materials using ultrasonics. Next. So my talks outlines is first introduction, objective methodology which we have used to characterize the materials, to analysis the materials, and materials which we did study, and physical conditions at which we study these materials, some essential parameters like elastic constants, thermal conductivity, divide temperature, specific heat, etc. And I will speak on different rare earth materials. Next. So, as you know that the ultrasonic uses very high frequency sound waves, and their frequency is above the 20 kilohertz. As you know, there are many destructive and non-destructive applications of ultrasonics. You know, in medical ultrasonic sonography, which will be under the application of ultrasonic waves, and you will see in mechanical engineering, especially welding, soldering, and others phenomena which will deal with ultrasonics. So next slide, please. Next. So we study the material. First, we should the structure of material. This type of material, either it may be face-centered cubic crystal, base-centered cubic crystal, body-centered cubic crystal, or hexagonal closed pack. And using different phenomena or different potentials like Coulomb and Warmer potential, Lennard-Jones potential, Morse potential, different interaction potentials. And we discuss their property of the material, and these properties are applicable for the quality assurance as well as for the quality control. Next, please. So research we did for the material. First, we analysis in presentation. We will speak on rare earth materials, some parameters, mostly elastic constant, some mechanical properties. In mechanical properties, Young modulus, bulk modulus, shear modulus, and thermal properties, divide temperature, thermal conductivity, and ultrasonic attenuation, energy loss when ultrasonic wave pass through the material, and how much energy will be lost. This loss will be discussed in this presentation, and analysis of the materials, and finally where these materials will be applicable. Next, please. So methodology for the computing the elastic constant. When the material on subjecting under varied temperature, the lattice expands, and thereby discontinuity arises in lattice. So lattice changes in property of the material. According to Broca definition, this is simply where U is the energy. This U energy is also sum of the energy at a constant temperature, zero temperature, and energy at a particular temperature at different higher temperatures. Next, please. So this is elastic constant is of two types. One is static, another is vibrational. Static means elastic constant at 0 degree Kelvin, and elastic constant at particular temperature like 100, 200, and 300. In this presentation, those materials we present here are governed by the interaction potential, Coulomb and Warmer potential. This is a Coulomb potential, as you know. This is nothing but Q1, Q2. जो आपका you know the Coulomb's law, and we use the Coulomb potential. Next, please. Material under study, we study the materials, actinides, some lanthanides. In those, there are two classes, monomictides and chalcogenides. These are two classes of the materials in which we use the nitrogen, phosphorus, arsenide, antimony, etc. Then those materials are termed as the nictides. If only one atom is share with the one atom of the actinide metal, then an actinide element, then materially termed as nictides. And if the lanthanide or actinide, these are mixed with oxygen, sulfur, selenium, tellurium, then these are known as chalcogenides. Next, please. There are some physical conditions. We study the materials under different crystallographic direction. As you know, in either BSc second year or third year in solid state physics or in MSc, you know the directions 110, 11 using the Miller indices. Why using the Miller indices? First you write the intercepts, then reciprocal of them, then taking the LCM of them, and finally you will get the directions. So study is in different directions and different at different pressure. Study is at from 0 to 8 gigapascal, and temperature range which we studied is 0 to 500 Kelvin, and at different magnetic fields 0 to 15 Tesla. Next, please. So these parameter determination. First of all we calculate or compute the elastic constant using the Coulomb and Borman potential. Then second order elastic constant will be used to compute the mechanical properties like Young modulus, bulk modulus, anisotropy factors, tetragonal modulus, shear modulus, Bridgely, nonlinearity parameters, and these parameters are very important for finding the stability of the materials. The material will be suitable for that particular place, particular temperature, or particular direction. And in thermal conductivity, using this elastic constant, density, and these parameters, we compute the divide temperature, pressure derivative of elastic constants, acoustic coupling constant, thermal conductivity, Gunnison parameters. Next, please. The essential parameter for finding the elastic constant is lattice parameter. As you know, for a student of solid state physics or solid state chemistry, दोनों में पढ़ाया जाता होगा. Lattice parameter, we use the simple nearest neighbor distance. In our case, nearest neighbor distance is a half of the lattice parameter. R0 equal to A by 2. In other cases, especially in FCC, other FCC metal, BCC, this is different for the different type of structure. If you study the body centered or face centered, then you will see the value of the nearest neighbor distance is different. We use a fitting parameters, which is hardness parameter. Next is density. These three parameters we will find the ultrasonic velocity, and ultrasonic velocity is applied to find the thermal conductivity and other parameter, specific heat, energy density, and finally ultrasonic attenuation. Next, please. So mechanical properties of the material, how it is responsible or how it is rolling an important role in characterization of the material, how these materials are applicable for the industry, how these material are applicable at particular place. For this, first we see the stability criteria. This is one stability criteria. These are two C11, C12 and C44 are the second order elastic constant, and these constants are used to find the stability of the material. Bulk modulus using this formula C11 plus 2 C12 divided by 3. If this is greater than 1 and shear modulus CS is greater than 0, and bulk modulus lies between C11 and C12 and C44 is greater than 0, then material is stable. Second thing is Cauchy relation. Cauchy relation at 0 degree Kelvin. These two elastic constants C12 and C44 are equal at 0 degree Kelvin. As temperature increases, this Cauchy relations are deviated because as temperature increases, there will be some disturbance in materials and their bonding covalent bonds will be disturbed and there will be new arrangement. So due to new arrangement, this Cauchy relation is not hold. So these are some formulae to find the Young modulus, Zener isotropy ratio, Poisson ratio, and anisotropic shear ratio. Next one, please. Another criteria for finding the either this material is soft or hard, either it is brittle or ductile, we use the Poog ratio or Poog indicator. Poog indicator is shear modulus divided, bulk modulus is divided by shear modulus, or shear modulus is divided by bulk modulus. If this value is less than 1.75, then material will be brittle. Otherwise, material will be, if this is greater than ductile, greater than 1.75, then material will be ductile. And this is condition for central force. If this condition is fulfilled by the material, then material is under the central force. Otherwise, it is not. In for non-central force, condition is given 0.23 to 0.24. As you know, the anisotropic, for the finding the anisotropic the material in different direction or at different temperature or other physical conditions, materials behave differently. The material is not isotropic. Material property will be different. If value of A, as you see the formula for finding the Zener isotropy A, if it is not equal to 1, then material will be anisotropic. Similarly, for finding the Lattice nonlinearity parameter, and these K1 and K2 will be found out using the second order elastic constant. Next, please. So ultrasonic velocity is another important parameter which is used for finding the structure or internal structure of the material, and it will be obtained using the second order elastic constant and density of that particular material, and this will be computed using these formulas. Thank you, sir. And next is divide temperature. Divide temperature is a significant factor which defines the division between quantum mechanical and classical mechanical behavior of the phonon. As you know, phonon is analogous to photon. In case of photon, photon is light quanta, while in case of solid state physics or crystallography, it is used as phonon. Phonon is lattice quanta. So divide temperature depend on the dispersion law. Using the theory, find the formula this theta d equal to h divided by kb, where h is the Planck constant and kb is the Boltzmann constant. 3q is the number. Q is 2 for the base centered material and 4 for the base centered material. It is different for the different type of materials. Next, please. So thermal conductivity, we also find the thermal conductivity using by two approaches. One is Slack and Berman approach, and another approach is Kyle approach. In case of Kyle approach, we use the ultrasonic velocities, and ultrasonic velocities are obtained using the second order elastic constant and density. And in case of Slack approach, we also use the second order elastic constant and third order elastic constant. This is gamma. Gamma is the Grunheisen parameter. And Grunheisen parameter, mathematically, it is simply formulations using the second and third order elastic constant ratios. Next, please. Ultrasonic attenuation, as I said in starting, ultrasonic attenuation, this is nothing but it is loss when ultrasonic wave passes through the material, then ultrasonic energy is converted to thermal energy or another type energy, then there will be some loss of energy. So ultrasonic energy is nothing but decay of wave as it propagates through the material or is passed through the material. In different type of solid, these are of many types: attenuation due to phonon interaction or phonon viscosity mechanism, and ultrasonic attenuation due to electron phonon interaction or electron viscosity mechanism, and loss due to thermoelastic relaxation mechanism, and loss is due to lattice imperfection. If any material is having some defect, either Schottky defect or Frenkel defect, then we find the losses due to the lattice imperfection. Next, please. So ultrasonic attenuation due to phonon interaction or phonon viscosity mechanism, equilibrium distribution of thermal phonon in solid is disturbed by the passage of ultrasonic waves. When ultrasonic wave is passed through the material, their equilibrium distribution of thermal phonons are disturbed, and re-establishment of equilibrium maintained by the relaxation process. And this process is entropy producing process. Simply, this is we use theory by the proposed by Accuser and further verified by the Budorov and Henrich. Finally, WP Mason developed this theory, and we use the simple formula for finding the ultrasonic attenuation or ultrasonic loss. And this loss is in the unit of either in decibel per centimeter, decibel per meter, or Napier per meter. And between these two units, there is a relation 1 Napier equal to 8.686 decibel. Next, please. Attenuation due to electron phonon interaction. Ultrasonic absorption due to electron phonon interaction occurs at the low temperature, because at low temperature mean free path of electron is as compared to the wavelength of acoustical phonon. When momentum of both are equal, then we use this phenomena using the electron phonon interaction, as most of the students who study about the superconductivity, they also studied electron phonon interaction via phonon using the BCS theory. Bardeen Cooper Sharifer theory, in which, but it is different from the superconducting material. It is applicable for all type of materials, basically on the base center material and hexagonal materials. Next, please. Loss due to thermal relaxation time. When an ultrasonic wave propagates in a cluster, there is a relaxation flow of thermal energy from compressed region to the expanded region. Associated with the wave, this thermal conduction between the region of the wave causes the thermal attenuation. There will be, when the relaxation flow of thermal phonon between the hot region and cold region, then there will be thermoelastic loss. Next, please. Attenuation due to dislocation damping. As in starting of the attenuation, I said you, dislocation, due to dislocation, there will be loss of energy. So this is also accountable by the as dislocation and screw dislocations, either using the Frankel defect or Schottky defect. Next, please. Next. So this is first case study, a mechanical and thermal properties of the Praseodymium monopnictides. So as we discussed, monopnictides, those materials which have a element nitrogen, phosphorus, arsenide, bismuth, those are known as the pnictides, and these pnictides are studied in this presentation. Next, please. So first, in first figure, we plotted the C11, C12, and C44 in case of first graph. You will see at as temperature increases, the value of the second order or elastic on C11 increases, and in some cases C12 decreases, as you are viewing by the red lines. And similar behavior is obtained for the third order elastic constant and fourth order elastic constant. Next, please. Next. And these graph for the bulk modulus, shear modulus with the different material, it is different for the different materials. And this plot is for the Cauchy relation, as we discussed in the starting. Cauchy relation at 0 degree Kelvin, C12 and C44 are equal, while as the temperature increases, then it deviated, because there will be some disturbance in the lattice, and so value will be different. Next, please. Next. So this is a graph for the Debye average velocity of Praseodymium monopnictides. Using the Debye average velocity, we use the formula for the different directions. Next, please. So this is graph between for the thermal conductivity, ultrasonic attenuation, basically all associated parameters: ultrasonic attenuation, ultrasonic velocity, thermal conductivity, specific heat, energy density, all are applied for the finding ultrasonic attenuation of the material. Next, please. So these are some conclusion as I said in presentation. Next, please. So this is next case for the cerium monopnictide. Next. In the similar way, second order elastic constant C11 increases while C12, these red lines are decreases with temperature. and divide temperature in the direction of 110 is highest. So material property or material will work in this direction most effectively. Next, please. This is Grunwald parameter graph of different materials. Grunwald parameter, these parameters are expressed as the diverse weighted averages of Grunwald tensor using and Grunwald parameters are obtained by the using the values of second and third order elastic constant ratios. There are after computation of this equation, we find the different Grunwald parameter, their average value and square average value, and then average square and average value are applied in for finding the ultrasonic attenuation. Next, please. Next. So this is graph for the specific heat and thermal conductivity, how thermal conductivity is related to the specific heat. And these all are applicable applied for finding the ultrasonic attenuation. You will see the right side top graph, and we also find the drag coefficient using the ultrasonic attenuation value. Next, please. This is some conclusions. The decrease in shear modulus, the decrease in temperature results the lattice instability, which leads to dislocation of the plane. Phonon viscosity or phonon-phonon interaction mechanism contributes directly to the ultrasonic attenuation and indirectly produce the damping of for the dislocation motion. And lattice thermal conductivity play the basis for the calculation of the dislocation damping, and we also use the value of ultrasonic attenuation via phonon-phonon interaction. Next, please. So these are some conclusion for second order for the ratio. As I told in starting, if ratio is less than 1.75, which confirm brittle nature of the materials. If this is greater than 1.75, then these materials are ductile, soft and hard materials. Larger the divide temperature, smaller will be the attenuation. It is by the theory, and in theory, it is reciprocal of the attenuation. So we say directly, if divide temperature increases, then ultrasonic attenuation will decrease. Next, please. Next. Previous slide. Order of the thermal relaxation time for these material is found to be the picosecond order. It is different order is different for the different type material. Either it is 10 to the power 11 to 10 to the power 12 second, minus 12 second. If it is 10 to the power minus 12 second, this confirms the semi-metallic behavior. If this is 10 to the power minus 13 second, then we say the material is semiconductor. So this is important for the classification of the material. Next, please. So this study for the plutonium monocalcogenides. In case of monocalcogenides, first graph, you will see the C44 and C112. It is increases as temperature increases, and this play important role for finding the ultrasonic attenuation. In ultrasonic attenuation, we see that at 200 degree Kelvin, it is uh, there is some drop of the ultrasonic attenuation. So this particular temperature is significant for these materials. Next, please. Next. Next. So there are some rare earth arsenide, neptunium and uranium arsenide. In these two cases, C11, C12, and C44 are given in the graph. As you are seeing, value of C11 increases with temperature, while value of and C44 decreases. Similarly, value of C11, C12, and C45166, these are decreases at 0 degree Kelvin is constant because these three values, value of C12, 112 and C166 are equal at 0 degree Kelvin. So these two values are equal. As temperature increases, then these values deviated. And this is also shown in next figure. In next figure, Young modulus is shown with respect to the temperature for the these arsenides. Next. So this is graph for the longitudinal and shear attenuation, and these attenuation is also known as ultrasonic attenuation due to phonon-phonon interaction. And third one is graph for the thermoelastic loss for the arsenides. And we see from these three figures, the thermoelastic loss is negligible in comparison to the other longitudinal loss and shear loss, or loss due to phonon-phonon interaction. So in this case, phonon-phonon interaction mechanism is predominant over the thermoelastic loss. Next, please. Next. So next is ultrasonic study in erbium monopnictides, erbium nitrides and arsenides. Next, please. Simply, first we computing the elastic constant, and we use a matrix, a MTEX programming using the MATLAB. It is available online. This is program for the program and finding the value for the input matrix for these material. Next, please. And we find the graphic visualization using the MTEX. In order to visualize the computed quantity, we have used MTEX, this software, and this software is available online. The computed parameter are plotted on the projection of the unit hemisphere for the ERAS. The graphical visualization for the based on the single crystal elastic constant, we use the elastic constant, and we find the value of how much value of Young modulus using these two pole diagrams. Next, please. Similarly, we can also obtain the ultrasonic velocity for these materials using the P wave and longitudinal wave and shear wave. Next, please. So assessment of anisotropy behavior of thermal conductivity is also being done in this case, and this is higher ERN is higher than that of the ERAS. Thus, conductive heat losses will be reduced in case of ERAS along 100 direction, which make it suitable for the potential application in the field of semiconductor. Next, please. Next. So this is case for the europium chalcogenides. In case of europium chalcogenides, we see the europium oxide, europium sulfide, and europium tellurides. In these materials, we also have the value of C112 and C44 are is same at 0 degree temperature. As temperature increases, their value is different. Next, please. Next. Next. So this is case for the terbium phosphide. In case of terbium phosphide, we plot the ultrasonic velocity for the terbium. So it is increases with temperature, and here we see in second graph the thermoelastic attenuation due to phonon-phonon interaction is first increases then decreases in different directions. So we find the maximum value along 100 direction. So 100 direction is not suitable because the loss we choose that particular direction in which we find the less loss. Next, please. Next. So there are some other materials, and this work is published in International Journal of Computational Materials Science and Engineering. It is Journal of World Scientific. Next, please. In this case, we find the similar result for the holonium nitride. So Cauchy pressure, which is nothing but it is difference of the values of C12 and C44. This help for the characterization the of the material, and Cp is positive for the metallic non-directional bonding and negative for the directional bonding. Next, please. Another parameter which we have calculated in this particular paper, hardness. As you know, the hardness is important physical property of material that reflect its resistance to elastic and plastic deformation, and we use the Beaker hardness using this formula G divided by P. Where P is the particular pressure and G is the shear modulus, which we obtained using the formula for finding the shear modulus. And the empirical malleability of the polycrystalline material is measured in terms of Hooke ratio, that is VYG. Next, please. And this is shown in the figure, in this figure. Next, please. Next. Next. So this is some comparative study of the many materials. We also compare all these materials and their parameters like second and third order elastic constant. Next, please. So this study at high pressure behavior of various rare earth mononucleotides or monocalcogenides using interatomic potential theory, that is using the Coulomb and Warmer potential has been investigated, or particularly these materials are cubic, especially face-centered cubic crystals. And knowledge of these properties is quite essential for many practical applications such as thermoelastic stress, sound velocity. As you have seen, the sound velocity is also calculated using the elastic constants value, load deflections, internal strain, fracture toughness, material characterization, etc. And Bridgely nonlinearity parameter is the controlling factor in nonlinear distortion of the sound in solid, liquid, and gases. The nonlinearity parameter for solid typically lie in the range of 0 to 16. In our case, this value is lie in this range and are relatively temperature dependent. On this basis of directional ultrasonic velocity, the anisotropic analysis of the materials have been carried out. Next, please. Assessment of the anisotropic behavior of thermal conductivity also being done. In most of the cases, we use two approaches. One is Kyle theory, another is Vickers theory. On the basis of thermal relaxation time, we can say the materials are either intermetallic valence, as I told in previous case. This material is semiconductor. If value of thermal relaxation time is 10 to the power minus 12, and we also did one of paper which is published in Central Journal of European Physics, in which paper we divide the material in three classes: one intermetallic, and metallic, and semi-metallic. Next, please. So you cannot inspect in quality; you must build it in. So using these parameters, we find the material properties, and by by knowing the properties, we find the material performance for using in industry or other places. Next, please. So these materials are applicable as you know the ultrasonic NDT, non-destructive testing. This is apply for the range of materials like metals, glasses, advanced material, in study of elements of applied physics, chemistry, environmental science, materials, magnetic materials, and electronic materials and devices. Next, please. So rare earth materials considered to be part of green technology industry, helping to improve the efficiency in magnetic, battery, glass, computer, etc. Spintronics, due to their unique ferromagnetic behavior and electronic properties, high performance computing, magnetic refrigeration, electro-optic components. These materials, most of the studied materials have the properties of the sputonic materials. Next, please. Composite lasers, phosphor lasers, nonlinear optics, electronics, photo optical devices. Next. So this is our special contribution. For this paper is published in Platinum Metal Review in 2010, and for this paper we received $110 for each author. And now this paper, this journal is published by the name of Johnson Matthey Technological Review, and it is SCI journal, and by your blessings or your best wishes, I am one of the editorial members of that particular journal. And they improve these diagrams. I have given the simple diagrams and separate diagrams. They all the merged diagrams are using the color for the different. You will see color of this is color like copper, because this is copper alloy, and this is color for silver alloy, and this is color for uh, gold. So they did this editorial work, and we will see in this case, as you will see in first case ultrasonic velocity, it is generally it is increases with the alloying, and in this case, in finally you will see the ultrasonic attenuation. As this is last one is you will see the platinum content is more in last one. So in this study, we emphasize that if we increase the amount of platinum, actually there are very important uh, metal platinum. Platinum group metals are very important and they are having cost very much high than the gold. So as we mix with copper, gold and silver, platinum, then performance of the material will be better. This is especially shown in this material, in this study. Next, please. Next. And second one, which we, next please. Next. Second one is we study the thulium mononucleotides. This paper is published in Central European Journal of Physics, as I said in presentation. In this contribution, we divide the material in three classes on the basis of their values of thermal relaxation time, ultrasonic attenuation. Next, please. On the basis of relaxation time, you will see the order of the thermal relaxation time for the thulium telluride, thulium sulfide, and thulium selenide are of 10 to the power 11, 10 to the power minus 12, minus 12 to minus 13. So these three values shows the material is either metallic, intermetallic, or semiconductor. So we divide the material in three classes: metal, intermetallic, and semiconductor. Similarly, the value of their value will be, next please. Their value of ultrasonic attenuation. On the basis of attenuation, the classification of material can be made. It is either metal, intermediate valence, or semiconductors, etc. Next, please. Next. So I acknowledge our supervisor, DPhil supervisor, Professor Dr. Rajaram Yadav. He is a professor at Allahabad University and former Vice Chancellor of Bir Bahadur Singh Purvanchal University, Jaunpur, Uttar Pradesh. And second one is my student, Dr. Vyoma Malla. She is in Vigyan Prasad, DSC. She did lot of work and she will to do the research work. Next one is Dr. S.K. Jain. He is my collaborator at NPL, Dr. Yudhishthir Kumar, Dr. N.R. Pawar, who always encouraged me, Dr. Girdhar Mishra, Dr. Dhiren Kumar Chaudhary, Dr. Puneet Kumar Dhawan, Dr. Shakti Yadav, Dr. Ramanshu Prabhakar Singh. These two are here. Dr. Ramanshu, please stand up. He is our youngest faculty member in physics department. And another one is Dr. Shakti Pandit and Dr. Dhiren Kumar Chaudhary. We received a grant from the UP government recently for the Center of Excellence in Physics Department and Center for Renewable Energy. Dr. Dhiren Kumar Chaudhary, he is coordinator of our research center. And these are some, I am also thankful to organizer of the conference and my well-wisher, especially Dr. Ajay Doble sir, Dr. Wagli sir, Dr. Pawar sir, principal sahab, etc. Thank you. Next.
for such wonderful treatment of fully on behalf of our community as well as the partners. Thank you. Now, so first of all, second benefit of Dr. Virendra Kumar Chaudhary. Dr. Virendra Kumar Chaudhary is working as a scientist, assistant professor, and head center for renewable energy professor at Rajendra Singh Institute of Physical Sciences for Study and Research, VPS Purvanchal University. He is coordinator of Center Research Facility, VPS Purvanchal University. He has significant research experience in the field of photovoltaic devices since he is a PhD and postdoctoral research work has based on the photophysical investigation of organic sky materials and fabrication of the photovoltaic cell devices. During his postdoctoral research work, he work on the growth of different kinds of polymers, perovskite films, and the study of the optoelectronic properties, application of the solar cell devices. In this order, we have also designed the initial setup for the growth of nanostructural halocyanine and perovskite films, demonstrated their effect on PVD devices. His work gives an insight into the growth of mechanism of nanorods and compact perovskite films. Such under the different solvent treatment during the postdoctoral study, he worked as a research associate in Center of Advanced Functional Materials, Indian Institute of Science, Education and Research, that is ISL Kolkata, for 1 year with the Professor Sayan Bhattacharya, where he worked as a on fabrication of the perovskite solar cells and synthesis of the perovskite quantum dots and nano sheets. Using the quantum dots, he designed dual strategy quantum dots treatment for the monolithic growth of the thin films. Also designed many perovskite solar cell devices. He worked as a project scientist in National Center of the Flexible Electronics in the Institute of Technology, that is IIT Kanpur, with Professor S.S.K. Iyer. Where he worked on the efficiency of the improvement in organic solar cell devices for the transition of the efficient organic solar cells on paper substrate. His field and he filed Indian patent as outcome of his research work, and research paper are in the queue of publication. Dr. Virendra has over 8 years of research experience in the fabrication of solar cell. He presently guiding 3 research students and 7 projects sponsored by different organizations. He has published 21 research papers, research articles, and 1 patent on his own field. Thank you, sir. So please, I heartily welcome you, and I request you to deliver plenary talk.
Yes. Thank you. Yes. Yeah. Thank you so much for the for inviting me, and I would like to thank the convener of the conference and principal sir for giving me this opportunity to discuss my few results work among the very young researchers and esteemed and very in front of very senior faculty members so that we can get some improvement and modification in further modifications for our future endeavors. So myself, Dr. Dhiren, and I am working as a assistant professor and scientist in Center for Renewable Energy. And today's topic is on building integrated solar cell. So I have means most of time I have worked on solar cell devices like organic solar cell devices and perovskite solar cell devices. So for young students, means organic solar cell devices are such kind of devices which used to fabricated using organic semiconductors, whereas perovskite solar cells are so those devices which are fabricated using perovskite material which are in ABX3 structure. So I will discuss very specifically on about perovskite solar cell devices and more specifically their uses for building integrated solar cell devices. I would like to explain what are building integrated devices. Like you can see here, some windows are here, and you know why we used to put these windows. We used to restrict some sort of sunlight to avoid we use this for avoiding some sunlight. What if we could utilize those avoided sunlight as electricity? So today's talk is all about that. So I'm not going in that much detail. So as I am working in Center for Renewable Energy, Center for Renewable Energy is involved in these activities. So in introduction, as fast growing population and dependency of human being on energy, it has been predicted that by 2050, the energy gap would be 15 terawatts. And we know we are prominently dependent on fossil fuels, which are very limited in on Earth. So we need to reduce this dependency on fossil fuels. So, therefore, as well as we have seen the use on huge amount of consumption of these fossil fuels, so some global reasons, some like greenhouse effects are appearing, which are hindering and our livelihood on this earth and increasing the day by day our what to say temperature of entire earth. So these are